A to B, okay, if we're looking from A to B, not that big of a difference. We know that the initial energy has to be equal to the final energy. Therefore, the energy at A has to be equal to the energy at B. Okay, that's fine. So at A, it's all gravitational energy. At B, it's gravitational energy plus kinetic energy. Now, be careful with this notation. This is the B side, this is the A side. So this is the gravitational energy at A. This is the gravitational energy at B. So it's not like you could subtract this from both sides. When I come over here, I know that this is going to be mgh. This is also mgh, but it's a different h again because you notice here that's a different height. So we're going to call this is the height at A, this is the height at B. Oh.
Happy birthday, Jimmy!
So and again, we see that the m's go away, and you can relate the heights here. So this is I'm going to subtract this from both sides. So this time, we're seeing that if you want to solve for V, you would need to know both heights. And in this case, it's actually the height here is just the drop height. So that's how that manifests in this case. There are times when we're going to manifest all three, kinetic, elastic, and gravitational, all together. So let's look at one of these situations. One of my favorite situations is the bungee jump situation. So let's consider a bungee jumper. So here's the ground, and our bungee jumper's on a tower. There's the bungee tower. Here's the jumper. Now, as this bungee jumper jumps off, say he just steps off, he's going to start falling. And he's going to fall, and this bungee cord is going to start catching him, and then it's going to bring him to a stop somewhere at the bottom. And so we actually have multiple locations where we're looking at the bungee jumper. One of the locations is here. That's the very top. The next location is where he's fallen. So this is right before the bungee cord catches. Okay, it's right before the bungee cord catches. The third location, is an interesting one because it's where the bungee jumper is in equilibrium. That's where the gravitational force down is balanced out by the bungee cord force up, the force of the spring upward. And the last one is where he's stretched all the way down. So in this case, we would say the velocity here is equal to 0. Here, the velocity is down. Here, he's still moving down. And here again, the velocity is equal to 0. So when I look at these, okay, I want to do an energy bar chart for each of them. So what does the bar chart for each of these look like? Well, this first one, okay, second one, third one, fourth one. We'll look at all three of our energies here. So there's gravitational energy, elastic energy, kinetic. So let's examine these. Before we start, we need to designate an H equals 0 so we understand what our elastic energies are. We have two good choices here. One of the choices would be to call this, the ground level, H equals 0. So here we'd have a large H, kind of large, medium, a very small h. That's one way to do it. Another way to do it is to call its lowest point h equals 0. If you call the lowest point h equals 0, that means here there's not going to be any gravitational energy at all instead of some small amount, and then each of these would be a little bit less. It doesn't matter, you can do what you want. Let's do that way though, because it makes things a little bit simpler. So if I call this right here, and I'm going to use the center of the bungee jumper here. I'm going to call that, designate h equals 0. Okay? And we'll call these points we'll call them A, B, C, and D. So what's the energy situation here? Well, they're actually kind of easy to figure out because does he have some gravitational energy? Yes, because he's high above the 0. Does he have any elastic potential energy? No, because the bungee cord is not stretched out at all. Does he have any kinetic energy? No, because he's not moving. So in this case, it's all gravitational energy. Here, he's falling. So when he gets to here, does he have some gravitational energy? Yes, he does, because he's still above the h equals 0. Is he moving? Yes, he is, so he has kinetic energy. But does he have any elastic potential energy yet? And the answer is no, because he hasn't started to stretch out the bungee cord yet. So in this case, we would say he has some gravitational and some kinetic because he's moving. However, these two are both small, but if you add them up, they equal this one. What about here? Well, he still has some gravitational energy, a little bit less than this one. He has some kinetic energy, a little bit more than the previous one. And the bungee cord has now started to stretch because this is where he's in equilibrium. And so he has some of this. So again, the total amount has to stay the same. So 1, 2, 3 has to add up to 1, 2, which has to add up to 1. And then this last one I love because he's at the bottom, so no gravitational. He's also not moving, so no kinetic. So that means all of his energy, so that one has to equal that one. So we look at those, and we can see how this thing manifests when we put all three of them together. Classic type of problem. Another classic type physics energy problem is just a pendulum swinging back and forth. So we're going to watch this pendulum swing. And our pendulum is going to swing from A to B to C. This one's actually much easier than that one because if we just examine the energies, as it swings from A to B, at A, well, the way a pendulum swings, we know that the velocity is 0 on both sides, so it has all gravitational here because it's not moving. Here it's all kinetic. And then here again it's all gravitational. So if we wanted to compare B to C or A to C, we know that because of the law of conservation of energy, the energy at A has to be equal to the energy at B. It's all gravitational. It's all kinetic. One half mv squared. And then we can see that the m's, m on both sides magically disappears, and we can see that again, the speed is only dependent upon how high you pull it and not dependent upon the mass of the object at all.